Welcome back. We're going to look at two more motivating examples for our study of differential equations. So the two that we want to look at here is the skydiver in free fall, and the next one will be heat transfer problems governed by Newton's law of cooling. Now I promise we're going to go into these in much more depth later on, but first let's just have a quick look at these. So the first one is the skydiver in free fall. So let's assume that the diver jumps out of the plane. And so first you want to ask yourself, what is the governing equation? What governs the motion of, well, pretty much any body that is in motion? Once you have figured that out, you might want to ask yourself as well, what forces are acting on the body? So, as we know from our study of dynamics, for an object that is in motion, we have Newton's laws of motion. And in particular, the one we're interested in is Newton's second law, which states that the sum of the forces is equal to the mass times the acceleration. Or in one dimension, we can just say that the sum of the forces, and we can say in the y direction, is equal to the mass times the acceleration in the y direction. Now, as you know, the best way to approach these problems is to look at a free body diagram of the problem at hand. So let's do that. So we have our skydiver here, who has jumped out of the plane. So you can think of probably a few forces that are acting on the body. So we have the force of gravity, or we could call this the weight. We also know that objects that are going through a medium such as air will encounter friction, or as we know, we call this air resistance or drag. And we're going to assume that the drag force is proportional to the instantaneous velocity of the skydiver. So let's draw this out on our free body diagram. So we have the weight, which is equal to the mass times the gravitational acceleration. And we have the drag force, which we are assuming is of the form kV. So, before we continue, what we need to do is set up a coordinate system for our Newton's second law. Now, the chosen coordinate system is fairly arbitrary, but what we can do here is say that y is positive downwards. So if y is positive downwards, then our Newton's second law will state that, well, we can see that the weight is acting downwards in the positive direction. So we have mg. And then the drag force is acting in the negative y direction. So minus kv. And that will be equal to the mass times the acceleration. Now recall that we're working with differential equations, so we might want to cast our acceleration in some sort of derivative form. So we could just say that the acceleration is the time rate of change of the velocity. So this is a plausible ODE that we would solve in our study of ordinary differential equations. And in fact, we will learn how to solve this, and the solution will give us the velocity as a function of time. That is what we are seeking. And what we will say is we want the velocity as a function of time subject to initial conditions. So initial conditions might be the original position or the original velocity of the skydiver. So you can think if the skydiver simply just falls out of the plane, then the initial velocity will be 0. Whereas if the skydiver dives out of the plane, then perhaps that initial velocity will be non-zero. Okay. So let's look at our final motivating problem, and that is Newton's law of cooling, which governs heat transfer problems. So differential equations appear in the study of heat transfer. So Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So let's write that out. So this is Newton's law of cooling. So the time rate of change of the temperature of a body is proportional to the difference between the body's temperature and the ambient temperature. And in fact, we usually include a negative sign there. The details of this will be covered later on in our study of differential equations. Here we have K, which is a constant, and TA again is the ambient temperature. So the above differential equation could effectively model the temperature as a function of time. So that is what we're seeking. So temperature as a function of time. And again, subject to initial conditions, and also it will be a function of our constant K and the ambient temperature A. So the differential equation could effectively model the temperature as a function of time of, for example, a hot copper ball thrown into a large water container, or maybe if you're into wine, so looking at grapes that are exposed to cold air or even potentially frost in the middle of the night, and to see what the temperature inside the grape might look like. But this is not a differential equation that is applicable to all heat transfer problems. So I want you to think about this. Is this an adequate model for the rate of change of the temperature of a human body, let's say, on a hot or a cold day? Think through this carefully and think about what changes we could make to this differential equation in order to more properly model the temperature of the human body. And again, we'll get into this in much more depth later on in our study.